So in this video, we're actually going to talk about drawing Lewis structures. Again, in a separate video, we're actually going to talk about the molecular geometry, electron geometry, etc. So the actual shape of the molecule. But for now, we're just looking at how do we draw Lewis structures and kind of form the pattern. So I want you to start off with the pattern that I use, and I promise you most likely you will never go wrong. So let's say in an exam you're given beryllium difluoride. Right? So how do you go about tackling the problem of drawing Lewis structures? So first thing I actually do is like count my electrons. So I say, okay, well, how many atoms do I have in the problem total? So I have, right? So with respect to beryllium, I have one beryllium and I have two fluorine atoms, right? Now let's talk about the valence electrons, right? In column 1 on the periodic table where you have hydrogen, everything in that column would be one valence electron. So they will have one valence electrons. Everything in column 2, so that starts with beryllium at the top, will have two valence electrons. Skipping the transition metals, going all the way over on your right side of the periodic table, starting with boron, everything in that column will have three valence electrons, and so forth. So you could see the pattern, right? Carbon and everything below carbon will have four valence electrons, right? So going over all the way to the noble gases, if you count, following the pattern, will give me 8 valence electrons. So beryllium is on the left-hand side of the periodic table again in column 2, and so that consists of 2 valence electrons. So we have 2 valence electrons, right? With fluorine, if you go all the way to the right side of the periodic table, you will see that it is just before the noble gases, and they are called halogens, right? So those will always give you 7 valence electrons. The reason why we want the valence electrons is because those are the ones that are involved in bonding, right? So now that I have the valence electrons from my periodic table, I could go ahead and count out how many total electrons do I have, right? So I have one beryllium atom with 2 electrons, so that's just two valence electrons. I have one I have 2 fluorine atoms with 7 valence electrons each, so that's 2 times 7, so that would give me 14. So in total, we have 14 plus 2, which would be 16 valence electrons. So let's go about forming the molecule. So usually in Lewis structures, what do you put in the middle? What is your central atom? It's usually the atom in front, to the furthest to the left. So it's usually, so let me say that usually, it's not always, right? So in water, H2O, oxygen is actually a central atom. But most of the times, the atom that's furthest to your left will be your central atom. So let's put down our beryllium, right? And we know we have 2 fluorines, right? So how do we go about forming a bond? Beryllium has 2 valence electrons around it. So in other words, it could only form 2 bonds in essence, right? So if I go ahead and form a single bond between my beryllium and fluorine on each side, well, now how many electrons I've used up out of the 16 total? Well, I have 2, 4, right? So I've used 2 and 4, right? So it's 2 and 2, which equals 4 total, right? Because remember, a single bond consists of 2 electrons. In this case, 1 from the fluorine and 1 from the beryllium. Again, in this case, 1 from the fluorine, 1 from the beryllium, right? Now, beryllium in this case is actually a special case. It does not satisfy the octet rule, right? So beryllium does not satisfy the octet rule, just like oxygen. I'm sorry, not oxygen, cancel that, but just like hydrogen does not satisfy the octet rule. So that's one of the exceptions that you just have to know. Now, for atoms such as or elements such as fluorine, chlorine, oxygen, nitrogen, those will always satisfy the octet rule. So again, we've only used 4 electrons out of the 16 that we have to place. So let's go ahead and fill, or let's go ahead and fill fluorine's octet, right? So I have 2 electrons on this side. I could put 2 electrons on this side. Again, I put 2 electrons on this side, right? Doing the same thing over here. All I'm doing is just filling in the total electrons. This is the only place I could put it, right? I cannot put these electrons on the central atom because beryllium shell is it's already full, right? Remember we said that we get 2 valence electrons from beryllium, so that's 1 here and 1 here. So beryllium cannot take any more valence, right? So let's go ahead and count fluorine's octet, and let's see if it actually satisfied the octet rule. So we have 2, 4, 6, 8. So that's good on this side. We have 2, 4, 6, 8. So fluorine is good, beryllium is good. Let's count now the total atoms we have in the molecule and see if that is equal to the total atoms we've counted, right? So you could see 2, 4, 6, 8, 10, 12, 14, 16, which is 16 electrons we see here. So we know that this is a plausible Lewis structure. This is a plausible Lewis structure for the molecule. Right, so there's a plausible Lewis structure for the molecule. A good way to test yourself on an exam to see if you're actually getting the correct answer is to check the total number of electrons that you've counted and the total number of electrons you have in a problem. So if we go ahead and clean this up, the Lewis structure for beryllium difluoride would look something like this. Right, and that's just me cleaning up. Obviously, the stuff that I erased earlier, that is what you'd put in an exam, right? But for just making it look pretty purposes, I guess, this would be the Lewis structures. This would be Lewis structure of beryllium difluoride. And again, going forward in the video, I'm going to represent the two dotted electrons as a single bond. Right, so they mean the same thing. Now, let's talk about carbon tetrafluoride. How do we draw the Lewis structure of carbon tetrafluoride? Well, again, I have one carbon atom, but I actually have 4 chlorine atoms, right? Now let's talk about the valence electrons. What about the valence electrons? Well, if you go to the periodic table, you see that carbon within that 4th column, excluding the transition metal from the left, has 4 valence electrons. And carbon is actually one of the special cases, but carbon has 4 valence electrons in this case. Right? What about chlorine? Chlorine is all the way over to the right, just before your noble gases. Again, everything in that column with chlorine will have 7 valence electrons. All right, and we kind of spoke about how to come up with the valence electrons from the table. So let's count how many total electrons we have in this case. So total electrons. So in this case, it's 1 times 4, which is 4 from carbon. But now we have 4 chlorine, so it's 4 times 7. So 4 sevens would be 28. So this would be 28 electrons coming from chlorine plus 4 from carbon. Right. So that would be 32 electrons in total that we have to place. Right. So remember again, we said that the central atom is usually your more the central atom is usually the first atom in the molecular formula, right? Which would be carbon. So let's go ahead and place our carbon. My pen is missing. Right. So let's go ahead and place our carbon. Right. Now we have 4 chlorines to place. So I'm just gonna go ahead and place my chlorine. Right? Now let's form our bonds. Remember, in each of these cases, most of the times, you will have a single bond. All I'm doing is just forming my single bonds at this point. So let's talk about how many electrons I've used thus far. So this is 2, 4, 6, 8. Remember, I said that one single bond counts as 2 electrons, right? One from chlorine in this case, one from carbon in this case, and one from chlorine. So we have 2, 4, 6, 8 electrons. Right? Now, carbon, again, is special that in most cases it has to satisfy the octet rule, right? So carbon's octet is full, right? We have 2, 4, 6, 8. So we can't put any more electrons around carbon. So the remaining electrons that we have must be on the chlorine. That's the only other place we could. That's the only other place we could put it. And so let's go ahead and start filling our electrons. So this is 2, 4, 6. Let's see how many electrons do we have around chlorine at this point. So we have 2, 4, 6, 8, right? Let's do it for the other chlorine. So this is 2, 4, 6. And let's go ahead and fill in our dots. Now, right? So I fill in my dot thus far, and you might wonder, like, how do I know? Remember, we said that we cannot place the remaining electrons on the carbon because carbon's octet is full. It already has 8 electrons around it, right? So if we take 8 minus 32, right? If we take 8 minus 32, that is 20. That is 24, right? So 8 minus 32 is 24. So we had 24 more electrons to place that did not include a carbon. So that means it had to be on the chlorine. Now, why didn't every electron go on one chlorine, right? Remember, chlorine has to satisfy the octet rule. That means it has to have 8 electrons around it at all times. So this would be 2, 4, 6, 8. So that's good. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Right? So let's count the total electrons that we have in this problem and see if it is equal to 32 electrons. Right? So let's see. 2, 4, 6, 8. So we have 8 that's coming from the central atom. And then we have 2, 4, 6, 8. I'm sorry. So let me say this again. 2, 4, 6, 8. So that's 8 coming from the central atom. And then we have 2, 4, 6. Okay. So this is 6 electrons around chlorine. And just going to multiply that by 4. So this becomes 6 times 4 plus 8. Right? So 6 fours is 24. Plus 8, and that's 32. Well, that didn't go so well, but this should be 32. Right? So you could see that the amount of electrons that I have in the problem is equal to the total electrons that we counted in the beginning. So that's why it's crucial to start to count the total electrons we have before we do the problem. That way we could check if we're actually incorrect or correct. All right, let's do another one. How about, let's say you're given boron trichloride. We're going about the same method. See if you can do this. Pause the video and see if you can do this on your own. Right? So I have one boron. Well, I just had beryllium. Well, so let me erase that. Right? So I have one boron, but I also have 3 chlorines. Right? Now look at the periodic table. How many electrons, valence electrons, does boron have? It actually has 3 valence electrons. Right? How many valence electrons does chlorine has? Again, it's a halogen. It's just before the noble gases, and we kind of spoke about it earlier. How do we get to that point? Is from the first element, from the first column, those will give me 1 valence electron. The second column will give me 2 valence electrons. Skipping the noble gas, skipping the transition metals, we go to the column with a boron ahead, and those will give me 3 valence electrons, and over where carbon starts will give me 4 valence electrons, and you see the pattern. So going to chlorine eventually give me 7 valence electrons. So if we count out the total electrons, right, I have 1 times 3 because I have 1 boron atom, which is 3 electrons, but I have 3 times 7, right? So I have 3 chlorines but 7 valence electrons each. So this is 3 times 7, so that's 21 plus 3. So in total I have 24 valence electrons to place. Right? So let's talk about a central atom. Right? Remember we said that most of the times our central atom is going to be the atom that's furthest to the left in the molecular formula. Right? So let's form our bonds. I have 1 chlorine, I have another chlorine, and then I have another chlorine. Right? So how many electrons we've used thus far out of the 24 that we have to place? So this is 2, 4, 6. Right? So we only have placed 6 electrons thus far. Right? Now remember this. Boron is one of the exceptions that you have to remember in your general chemistry classes. It does not satisfy the octet rule. So do not try to force an octet rule around boron. It simply does not work. It could only form, because of its valence, it only has 3 valence electrons. So just remember that this is an exception. So we formed 2, 4, 6 electrons out of the 24 that we have to place. So we still have 18 electrons to place. So at this point, I'm gonna use my single bonds as 2 dotted electrons. So, well, actually, let's not make any confusion. Let's use our dots, right? So this becomes 1, 2, 1, 2, 1, 2, right? So let's count the number of valence electrons we have around chlorine. 2, 4, 6, 8. So that's good. Let's do this again. We still have a couple more to place. Let's count the number of electrons we have around chlorine at this point. 2, 4, 6, 8. So that's good. And around here, let's do this. Right? So this also fulfills the octet rule, because remember, chlorine is one of those atoms or elements that has to fill the octet rule. So this is 2, 4, 6, 8. So that's good. 2, 4, 6, 8. So that's good. 2, 4, 6, 8. So that's good. Now let's count the total electrons we have in this problem and see if that is equal to 24. So we have 2, 4, 6 around the central atom. So that's 6 electrons plus we have 2, 4, 6 around chlorine right now. But remember, we have 1, 2, 3, right? So this would be 3 times 6 electrons, right? So 3, 6 is 18 plus 6, and that is 24 electrons, which is exactly what we counted initially. So that's why, again, get in the habit of doing these calculations first before you draw a Lewis structure. That way you can know if you're getting the correct structure. Right now, you could count this a different way. You do not have to count it this way. You could say, okay, well, to yourself, this is 2, 4, 6, 8, right? And then pretty much we have 3 of these, so this would be 3 times 8, right? So 8 electrons in total, and we have 3. So 1, 2, 3. So 3 times 8 again will give you 24. Let's do another one. How about the Lewis structure for xenon difluoride? How do you draw it? All right, how do you draw the Lewis structure for xenon difluoride? Well, let's do the first thing we're going to do again is do our calculations, right? So we're going to do our calculations. So we have 1 xenon atom and we have 2 fluorine atoms. Again, we said from the periodic table that xenon is actually a noble gas, and so that will give me 8 electrons, right? Fluorine is just beyond it, and that will give me 7 valence electrons. Okay, so if I count out the total electrons that we have, it is xenon, which is 1 times 8, but we have 2 fluorine atoms, so that's 2 times 7, so that's 14 plus 8, right? So that's 14 plus 8, and 14 plus 8 is 22 electrons. So we have 22 electrons to place. Okay, so our central atom again is usually the atom in first place, or the atom furthest to the left, and let's form our fluorines. All right, so let's form our single bonds first. All right, at this point, I'm just placing electrons. All right, so I've used 2, 4 out of the 22 electrons that we have to place. Right now, xenon again, it's a noble gas, so most likely you're going to have to fulfill its octet. It has to satisfy the octet rule. Fluorine again has to satisfy the octet rule. Right now, I only have 2 electrons around fluorine, so let's fill in fluorine valence. Right, I placed 6 electrons because I already have 2, so that will give me 8, right? 2, 4, 6, 8. Again, the other side of fluorine will be of no exception. Right, sorry about that, guys. All right, so the other side of fluorine will be no exception. It's kind of crunchy here, but you get the idea. This is 2, 4, 6, and then we have 8. So fluorine's octet is full on this side, and fluorine's octet is full on this side. So how many electrons total we've used thus far in the problem? We've used 2, 4, 6, 8, 10, 12, 14, 16. Well, fluorine valence is full on both sides, so the only other place that we could put the remaining electrons is on the xenon atom. That's how I want you to look at this problem. And so the only other place we could put the remaining electrons is on the xenon atom. Remember, we've counted 16 thus far, but we need 22. We have 22 total. So the only place we could put the electrons is on the xenon atom. So this would be 2, 4, 6. Right? And so if you look at xenon now, it becomes 2, 4, 6, 8, 10. Right? So we have 10 electrons around xenon, right? And we have the fluorine to satisfy the octet rule. So I apologize if I said earlier that xenon is one, but xenon is one of the exceptions. I apologize for that, right? But you could see here that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we have 22 electrons in total. So to clear this up, the lowest dot structure for xenon difluoride looks like this, right? Again, the number that we counted matches exactly what our total is, right? Let's try one more and see if you can do it. And pause the video before you actually do it. SI6, sulfur hexa iodide. How do we do it? Right? I look at the amount of atom I have. So I have 1 sulfur, but I have 6 iodine. Right? So we go to the periodic table, we see that iodine again is one of your halogens, and so that constitutes 7 valence electrons. Right? So iodine, that constitutes 7 valence electrons. Right? When we look at sulfur, sulfur is oxygen's cousin, just below oxygen, and that's in column 6. So that sulfur gives me 6 valence electrons. So let's count the total number of electrons we have. So total number of electrons. So total electrons, right? So we have 6 times 7. 6 times 7, that's actually 42. So we have 42 electrons plus 1 sulfur atom. So that's 42 plus 6, right? So in total, I should have 48 electrons in my lowest dot structure. All right. So let's go about forming our atom or molecule. Right, so we have sulfur in the middle, but we have 6 iodines around it. So right, so I have 1, 2, 3, 4, 5, 6. They're all single bonded. Right, so let's see how much of the electrons we've used out of the 48 thus far. We have had 2, 4, 6, 8, 10, 12. Right, so we've used 12. We've used 12 out of 42. Right, so we've used 12 out of 42. So I'm sorry, 12 out of the 48. Right, so we've used 12 out of the 48 total electrons that we have here. So we still have 36 to place. So where do they go? Well, we know that iodine is one of the halogens, and again, that has to satisfy the octet rule. So let's go ahead and satisfy our iodines first, or iodine, however you want to pronounce it, before we deal with the central atom, right? So again, I'm going to replace my dots as single bonds, but they all mean the same thing. This is still 2 electrons, this is still 2 electrons, this is still 2 electrons. Again, on the exam, if your professor says that okay, do it, but most of the times your professor wants you to actually put in your dots, right? So I'm just doing this for to just make it look better, but it's the same concept. So around this iodine we have 2, 4, 6, 8. This iodine again 2, 4, 6, 8, and I'm just gonna do the same thing around each iodine. Right, so I know the iodine makes it look really confusing, but you get the idea. So we have each iodine or iodine, each iodine atom or element has 2, 4, 6, 8 electrons around it. So if we have 8 electrons around around each iodine, and we have 6 of them, let's do 6 times 8, right? So 6 times 8, if we multiply 6 times 8, that is equal to 48. Right, and that is the total number of electrons we see here. Right, so no need to worry about the central atom. So the thing you might ask yourself is, okay, well, my professor is telling me, okay, the octet rule has to satisfy and all this stuff. Remember, there's a few exceptions that you have to know. So we talked about, well, obviously hydrogen. Hydrogen could only form 1 bond because it has 1 valence electron, so that will never be able to form an octet. Another common one you'll see in your classes will be like boron. Boron, again, we spoke about it earlier. It only has 3 valence electrons, so at maximum it will only be able to constitute 6 valence electrons total around it, so it will not satisfy the octet rule. The other exceptions that you must know is phosphorus, sulfur. You must know phosphorus and sulfur, right? These are what we consider sometimes expanded octet. So they do not have to satisfy the octet rule, meaning they could have more than 8 electrons total around it. All right. And then we spoke about boron, again, hydrogen being not expanded, but again, less than the octet. Right? So in your classes at this point, these are probably the 4 elements that you must know. Okay, well, these are exceptions to the rule. All right, and this is all we got. And again, remember, this is just pure Lewis structures. We're not looking at electron geometry, molecular geometry at this point. We're going to do that in a separate video.